This video is going to cover cochlear implants and the bilingual brain. To start off, a cochlear implant is an electronic device that partially restores hearing in people who have severe hearing loss due to damage of the inner ear and who do not benefit from hearing aids. Right here you'll see a diagram of a cochlear implant that shows the inner parts and the external parts. So you've got the external processor, the external magnet, the internal magnet, antenna, and receiver/stimulator. There's an external microphone. Internally there are electrode array, which is the wire that goes into the cochlea. You've got an external processor and an external battery pack. The electrode array sends the information from the processor to the auditory nerve. The brain uses this information in a similar way to a normal hearing person would interpret sounds. It takes several years of therapy and rehabilitation for an individual with a cochlear implant to learn to associate the stimulus they were receiving from their implant with language. Today, as many as 80% of deaf and hard of hearing students or children are receiving at least one cochlear implant via unilateral implantation. Now, since we're discussing bilingualism, we're going to discuss sign language as well, which is a system of communication using visual, gestural, and signs, such as that used by the deaf community. American Sign Language is the visual language used here in the United States. And here are some stick figures of a couple of ASL signs, so visual, gestural, and signs. Now we're going to discuss the auditory cortex, which is the portion of the brain for a long time believed to be solely responsible for spoken language input. So over 100 years, this is what was believed. Its location is close to the ear, and that contributed to the belief that sound was an essential stimulus for the auditory cortex. However, with current brain scans, with improved technology, it is shown that this area of the brain is actually active in individuals that have never received auditory input. Which disproves that spoken language is necessary for developing the auditory cortex of the brain. So this discovery has led to scientists believing that the function of the auditory cortex is actually to respond to patterns found in language. In that case, it wouldn't matter if the input was spoken or visual language, since these types of patterns can be found in all languages. This has been a big discovery in the field of language development, and has led to further discoveries on language development in general. They've taken groups and compared language development of different types of language learners, such as monolinguals and bilinguals and multilinguals. They've looked at their brains to see how their language and auditory cortex has developed. And we see that the language tissues are actually developing at the same rate. They'll hit the same milestones at the same time, as long as there is sufficient stimulation. So now we're going to talk about cochlear implants and bilingualism. So at the beginning, when cochlear implants became popular, the belief was that in order for the auditory cortex to develop properly and for the implantee to develop spoken language, they should avoid using sign language because it would interrupt the sequence of development of the auditory tissues, which they believed would lead to a oral delay, so spoken and listening skills. However, current research is contradicting this view, showing that prior to implantation and after the procedure, there's a rehabilitation and training period in which children are missing out on their critical language stimulation before the implant is actually functional. This lack of stimulation has led to an atrophy in the language center of the brain. So here we see the bilingual brain, where ASL and English is used, and then a monolingual brain. There should be a red dot. It would be smaller. It doesn't actually atrophy and go away. It should just be a smaller dot. That was my mistake. So a lack in development in this area could lead to cognitive, social, and linguistic delays. When we compare children's brains, when we look at their scans, to children who had early access to sign language with those that were not allowed access to sign language, we see that the group that had early access, they have stronger literacy skills. This is likely due to, in order to use the visual language of sign language, they have to develop an eye gaze. And this eye gaze, this skill is actually being transferred into reading. So those individuals are more efficient readers. And also with early stimulation, you have early development of the language center, which will lead to an easier development of English skills later on. This project was completed for my Education 760 class as part of my policy action assignment. I'd like to give some special considerations to the visual language and visual learning, VL2, and brain and language laboratory for neuroimaging, the BL2, which are two groups at Gallaudet University conducting research under Dr. Laura Ann Petito. I'd like to thank you guys for everything that you do. Additional information on the research or any questions you may have can be found at vl2.gallaudet.edu. And the resources I used was an article by Humphreys, published in 2013, which is Schooling in American Sign Language, a paradigm shift from a deficit model to a bilingual model in deaf education, as well as a webcast put out by the VL2 and BL2, which was directed by Dr. Petito. They focused on what the eyes reveal about the brain as far as advances in human language acquisition. which was published on May 1st of this year, 2014. And that's my name. Thank you for watching.